In the last video, we worked on clustering. In this video, we are going to work on anomaly detection techniques. We've been working on this sort of piece by piece. Outlier detection for a single variable is like the simple case of this. When we were looking at clusters, now what we're going to try and do is say those that were in the cluster are the ones that are normal. Those that are outside of the cluster are the ones that are not normal. And so we're going to go through here and do the same sort of thing we did with clustering, but then apply it to a separate set. Okay, so we're using the same data set here. And as a reminder, now it'll look like I just magically changed everything. That's because I just deleted things to clean it up. And if we look in here, I've got the same company data set with the latitude and longitudes in here. The same things that we could apply to clustering, we can apply to this anomaly detection technique. And we'll go through some of the details here. We're just going to use the simple versions, and then we can apply more of that later. So to start, we're just going to do clustering, or the sort of anti-clustering, I guess, the isolation forest based on longitude and latitude. And there are multiple ways to do these anomaly detection techniques, or there are different techniques. We're going to use this one called isolation forest. It's in the IsoTree package. There's a write-up available that you can read. But in terms of concepts, it's the exact same of what we did in terms of k-means clustering. It's just finding the part that doesn't belong. So I take in just the longitude and latitude. That's going to be what I'm going to work with. In contrast with the k-means version that we used, isolation forest can use missing values, and it can use categorical, non-numeric data. So if we're going to do non-numeric, we have to change it into a character. So if you have something in there that you're going to use that is not numeric, you need to change it into character values. But here I'm just using these two. Sometimes if we do a lot of making these trees long and to fit the data really closely, then it can take a long time to run. So there are a few ways to sort of deal with that. One is to use fewer variables. So if you use a lot of variables, it takes longer. Another is if you use lots of data, it takes longer. So to cut it down a little bit, I'm going to only use 30% of the data. And this sample underscore frac, so this is sample fraction. So in the function is what percent of the sample or data set you're going to use. I'm going to use 30% of the data set. So when I run this, you will see that temp2 is 30% of temp. That'll just make it faster to do all of this isolation forest stuff. In the end, you may want to run it on everything, or you may want to train it on a small set and apply it to a different set. But to speed it up in this, it's worth cutting it down some. If the distributions are similar across data sets, then it won't make much difference. If they're very different, then it will. And the set seed here is to make sure that we all use the same random generation that generates the random sample here. And so if you set the seed and we have the same seed, then the same sample, we'll get the same sample with this sample fraction. Okay, then I'm reading in the coordinates data just because I'm going to plot these on the map again. And this is a reminder of what all of the sample points look like. So we had seen this before, but this is all of the all of the observations in the data. So it covers lots of the US and Europe and Asia, and then some more parts. So how the isolation forest works is we have whatever data set we have. In this case, it's just these two columns. But whatever columns we're going to use for this approach, it's going to take that and then split it into different pieces until it finds ones that don't seem to fit with other observations. And this is the isolation forest function, and that comes from the isotree package. So you do need to read in, install, and then add into your library this isotree package. Isolation forest, you take the data set or the data frame that only includes the things you're going to use for forming the isolation forest. All of this is going to be read out. I should have done an assignment operator. All this is going to be assigned to this object that I'm calling model MDL, and then there are options that you can add to it. So these are I'm using, and we'll adjust throughout, but I'm using these ones to make it simple and to run faster, but we can use lots of different options. You can just use the default, which is isolation forest and then the data frame, but it will run a little farther or longer in some ways and then shorter in others depending on the choices you make. So let's walk through some of these choices and then we'll try some different ones as we go through. So seed is, again, this is a random number generator. If we use the same seed, then we can get the same output, or at least close to the same output. Number of trees, so it's a forest, meaning it has multiple trees. If you just run one, it'll go much more quickly. Typical might be 100 or 500 trees here. The benefit of having more trees is that it isn't left to sort of one random tree that it created. So hopefully more trees means it's more robust in terms of outliers that would be outliers no matter what tree sort of number or what different columns you use. There are different scoring metrics. So this one is depth. That's one we'll use here for a little while, but we could use one of the other ones as well. And I think we'll do another one below. The starting one that began with this is depth, but there are other ones, density and boxed. I forgot what it's called, but different versions for that. And then the depth is how many times we split the data to go down in the tree. So, think about a tree and its branches, that it's going further and further on those branches, and that's splitting up the data more and more times. And so if you split it up more times, then it's going to fit the data really tightly. If you split it up fewer times, it's going to fit the data less tightly, but it's going to run faster. So we may want to try some different things. Maybe typical is 5 to 10 here, but with large data sets, you could keep going and get a decent portion of the data in terms rows could be split down. So the more rows you put, the bigger the depth, the more closely it will fit the data, and the fewer observations will be in each group. So we'll mess around with this one a little bit as well. If you fit the data, the model on the full data set, then you can output a score here. This output underscore score equals true gives you a score for how anomalous any variable is. When we use it on a small subset and then want to apply it back to the larger subset, then we can't use this and we have to try something differently. Okay, so we run this. It runs fairly quickly because we're using only one tree and 3 levels of depth, and we split it down to a smaller data set. Now let's look over here, sort of what comes out of it. We get some parameters. This is how the trees are split. Then these other things about how many columns and things that we use. Number of threads, you can run this in parallel so that it runs a little quicker. And then output is the scores. So these are for each observation, this is the score that it has for those that are more or less unusual. Larger values mean more unusual, smaller values means less unusual. And it tries to fit these, at least for when we're using depth, around 0.5. So we could look at a summary of this just to give us an idea of what came out of the model that we ran. and it says it was a model, and the length is how many outputs it came with it. There are 9,070 scores, and it used the isolation for us. So not a whole lot of interesting here for us, but it tells us what we just ran, and then we'll see how we can get some of the output out of this. So I'm going to create a function that will repeat the same set of outputs over and over, because we're going to do the same thing over and over again. That's pulling stuff out of the model here. That's what these two parts are. Reading them into the data set we just used. So starting at temp2, add that back in, and then filter it to get only a certain subset, and then graphing it. So I'll go over slowly what this is, but this is just to set up the analysis every time we run one of these models. And then notice here, I call this summary function, and I have an input to it, and then I do it again, change that input, and it's going to do this every time. So this is just to save the amount of coding, repeating the same thing over and over. So let's walk through what happens on each of these. So this model $scores. So within the model output, there are these scores. So at first I want to summarize them and see sort of where they lie on the what their distribution looks like. So notice their mean and median are around 0.5. That's sort of what we would hope. Above 0.5 is supposed to be sort of high. And, here we could look and see what we would think are high. Well, at the 75th percentile and above, it's listed as high. Maybe we want a cutoff even larger, so we can look at the quantile function, and we could look and see at the different percentiles what is high. So notice at the 80th percentile it's 53. Well, as we get higher, we get fewer that are listed as high. So if we made a cutoff, let's say at 0.62, then that would only, like we said, above 0.62 is an anomaly. Then we have only 1% of the data that's going to show up as an anomaly. Whereas if we go all the way down here and we say it's 0.5, then 25% of the data is going to be called an anomaly. Then what I do is read back in those scores. So the scores here we had, take them from the model form output and read them back into the temp2 data set and call that object or the column anom score, so anomaly score. And then after I do that, I'm going to filter by some cutoff. That's the input. So if it's above 0.5, then I'm going to filter out and only keep those that are above that cutoff level. And I can change that cutoff level. And then I'm going to do a typical plotting. So plot the map stuff that we already have. And then from that data frame that I just created, anom here, plot the longitude and latitude of those outputs. Well, let's look at what that looks like. So if I do here, I read in the anomaly score back into temp2. Oh, whoops, I don't have a cutoff though. So let's do so call cutoff level this. The reason it's not that because I'm going to eventually run this in the function, and the function tells it what that cutoff should be. But if I run these, now notice in temp2, it created an anomaly score here. Anom is now, it cut off, any above 0.5. Now we have 2,500 that are above 0.5 out of the 9,000 we had before. Then once we run all of this, then it's going to plot this longitude and latitude from this smaller set that we called anomalous, right? So if it's above a certain cutoff level, we're calling it anomalous. So it's going to plot just those that are anomalous. And then the last part that it's going to output is a list that is A, which is the summary of the scores, B, which is the quantiles of the scores, and G, which is the plot. Okay, so this is just to simplify. Of course, you could just run each of these pieces in the function. especially if you're not going to do it over and over again. So I run that to create the function. Notice now the function came up down here, and it didn't do anything because I haven't run the function yet. So now here I say, okay, let's do the summary function, and let's make the cutoff be 0.5. So remember, 0.5 gives us about 25% of the data being an anomaly or being called an anomaly because the score is above that point. Let's go ahead and run this and see what happens. So notice at the bottom here, we had the output of the summary of the scores, and we had the different quantiles of the scores, and we got printed out here observations that were anomalous. Well, if we compare that to what we had before, notice we had all of the US, and then we had little clumps here and little clumps here. Well, using this anomaly score, we still have a lot that we called anomalies, which we may not want, but those that are in the southern US are the most anomalous. Those that are in, it turns out, sort of higher north in Europe are anomalous. And then we have others out here that are anomalous too. And that's just based on where the bulk of the data is, right? The bulk of the data is really in the northern US, and so, or at least the headquarters for the companies. So that means anything outside of the northern US sort of gets picked up as anomalous. Well, if we want to be more detailed, instead of finding certain points, we might change some things. So one way we could do that is to say, well, some of these are not as anomalous as other points, right? So some points could be really anomalous, other points less anomalous. So we could change the cutoff level and not have as many points on here. So if we change the cutoff level, run the function, the same thing's going to happen. And now notice with that cutoff level, it's only the southwest United States that's very unusual. Up here in, it's hard to see, Nova Scotia or sort of, Canada area. And then the Northern Europe is the sort of next anomalous part. So we've got parts that these are outliers compared to the bulk of the rest of the data. Well, then you say, well, why are these the most unusual, but we don't have some of these out here that are unusual, in the islands or other parts out here? Well, that's just because they had observations that were closer to them than these ones did. So we can start to mess around with these and try and figure out what we really think the cutoff should be, but this gives us a good start. So let's change a couple of things that we can do. So before we had max depth of 3. So that was when it was making it, this is sort of like saying very few clusters in the data. Here we're going to have many more, so that it's going to be more detailed. And so if we slice it up a lot, then we can have a cluster in, let's say a cluster in North Africa, and then it won't be as, ones that are close to that won't be as unusual. Or we can have southeastern United States have its own cluster that then maybe these won't be as unusual. So we're trying to just keep working through this until we find things that make sense to us. So we do the same thing, run this with 100 depth in terms of how many times it'll split the data. Only one tree, so it still doesn't take a long time. It was longer than the other one, but you can't really tell because it was fast enough. Then let's do the same cutoff of 0.5. So what happens this time? So we can look here at the output. Notice the max score increased a little bit, but the average score, this went down a little bit. So when we look at the percentiles here, notice it isn't until we get to the 85th percentile that we go above 50. So fewer observations are named as anomalous here, and that's because we have more clusters that allow things to be closer to those clusters. So here we see now there are many more in the United States that can be anomalous, but that's because it's relative to whatever area they're in. And then same thing with other areas, so some more have popped up. If we now make the cutoff higher, we want the ones that are most unusual, given the clusters and stuff we have. Now notice it sort of changed what it thinks is unusual. So now it's out on the west coast and still up here. And we've got some on the islands that are unusual. So now we start to get things that are unusual because of their distance from local clusters rather than from some global cluster. Okay, so then what else can we do? Well, we can also change the number of trees. So some of this, the anomaly stuff that we see among these spots are because of the particular one tree that was created. Well, if we run this through more times, then some of these may not be robust to the particular tree. So we run this, we can look again and see if we get something similar. And we'll do the 0.5 cutoff again. And notice it cleared out a little bit of the US. A few other spots changed. So some of the things that were in that one single tree didn't quite hold up when we ran it across multiple trees. Increased the cutoff again. And notice we've got quite a different picture here. So we still have some down here on the southeast of the United States, but notice a lot of those really are coming from islands down here, not from actually the continental United States. And we have some from the Mexico and southern part of the United States that we didn't really see before. And there are some other clusters around here, or anomalies of ones that are anomalous because they're sort of in the middle. You know, they're not near the clusters that they apply to. So here, these ones are unusual because, you know, these ones over here were normal. These are not normal. Same thing over here in India and other areas. Same thing with these islands down here, right? So we've got different parts that are now labeled as anomalous because we're looking at robust clusters that all fit together. Okay. Let's try something else. Let's do density as a different measure. I'm going to change to the max depth of 50, keep with 100 trees. And the reason I reduced it to 50 is because we want to keep it from getting, you know, from taking long to run. But we could change that too. And run it again. And here the cutoff is different. When we're using density, the cutoff is different. So they're generally positive. The cutoff could be 0 or 1 or, you know, something like that. We have to tell it something because of how we ran this before. But what I would do is check and see what the scores are beforehand. So what comes out of it is you see a lot of them are below 1, and then one that is really large. If we look here at the 95th percentile is where we start to see those cutoffs of greater than 1. So we're sort of imposing that they're more extreme by using 1. But notice that the picture changes again. It's sort of the same idea in all of these, which is good. It makes us feel good that however we change it, isn't going to matter a lot. But they are sort of different, so we want to try different approaches. And the main difference here is, again, this is sort of like when we used like we're keeping the idea of more trees. Some of this gets washed out, and the density changes a few of the spots, but in general, it's sort of the same. We can up the cutoff here to, let's say it's above 98, the 98th percentile, so only 2% are abnormal. You know, we could look and see what does that look like. And again, we're back to sort of what we had before of the higher cutoff with more trees in it. All right, so I mean, we're starting to get like, there are some areas, you know, some observations. There's clearly one here that is unusual, clearly something down here that's unusual, and you know, some in other parts over here that are unusual. So we can start to see those that in terms of where they're located, right? Just latitude and longitude only. They're unusual because they're in places where there aren't a lot of other companies. So this is headquarter locations that aren't around a lot of other companies. So let's say we think we have the right model. So, I would, in practice, what I would do is you'd go back through and try a bunch of these versions until um, you either learn something from it, or what what you have is you're satisfied that it sort of matches what your intuition would be and something you could sort of conceptually understand. So let's say we're now, somewhat satisfied with the output we have. So we're going to run this um, same approach with 100 trees, 50 depth, and this density approach, measure approach. Well, we cut it down to temp2 to be able to use the smaller data set, so 9,000 observations. We would really like to apply this to the 30,000 observations. So how do we do this? Well, we first have to set this output score to false. That way it creates a model and not a list of scores. So when we look at this model output here, it's going to use these parameters here. Notice it doesn't have scores down here. And then the reason we have to do that is because then it will allow us to do a prediction. So we have this predict.isolation underscore forest. This is just from a typical predict function, which we'll use some more later. And how predict functions work is to say, take the model that you've created, that's this MDL from the isolation forest, apply it to the whatever data set you're going to use. So I could go all the way back to the first data set, which would be this D set here, or I could go back to the temp data set. Doesn't really matter. Depends on what you want. So let's say we take it back to this D set, the original data set. So predict with this model to the original data set, and what it's going to predict is the score of how unusual it is, and I'm going to call that anom score here. So we run this. Sorry, I forgot that temp2 had this anomaly score in there because I did it up here in the function here that create a new column in temp2. So we can't use that. That's not actually part of the model, so we can't. If I try and train something on temp2 again, it's going to think that should be in there. So, so how I take that out is to then do temp2 remove anomaly score. Okay, so now that that's gone, sorry, that was the problem. So you should just have the two columns here. So I got to run this again now. And now if we do the predict with this back onto the main data set, it'll take those two columns, create a prediction. Now notice when we open this, we can go and sort and see different anomaly scores, high versus low. So now you can finally see there are some negatives in here. So anything above 0 in this case is supposed to be anomalous. Of course, you could set different cutoffs depending on how many you want to have in here, but somewhere in this range it starts to become anomalous. And then of course the most anomalous are the ones we really care about. So maybe some of these up here. So let's look and see. So we've got Durbanville, Brisbane, Australia, right? So we've got different places that we would call that are unusual because they're in places that a lot of other companies are not headquartered. So let's look at the least anomalous. Let's see what shows up here. Headquarters in New York City are least anomalous. So we have a lot of companies in New York City. That's part of what is causing that. So anything not clustered around there is sort of being labeled as anomalous. So the main point here then is that we're going to take these columns, whatever they are, and work with different inputs to the model, or different ways to train the model to come up with those that are unusual given the columns that we have. And of course that'll change depending on the columns we put in there, right? So, and that's what we'll sort of work on next, is what other columns might we put in there, and how might that help us find things that are anomalous, and do we need to fine tune that or not?